So I would like to thank for the invitation and for the opportunity to speak. The reason that BV is interesting for derived geometers is that it is one of not so many examples that encode both derived and stacky information. So you have this conjugate part, and you have this longitudinal. Longitudinal or Chevalier-Allenberg or Lie algebroid. So what's the conjugate part? Well, this is resolution of the derived critical locus of Lagrangian. So you can think of it as DG manifold or as a derived scheme. So in a sense, it is trivial because all the higher homologies vanish, but it's still a derived object. And this longitudinal, it encodes some action of some symmetries on the space. So you can say it's a stacky object, yes?
Just to mention, please assume we don't know what is the derived scheme, for example. You can see that?
Yeah, but so I said DG manifold, so it's algebraic version, let's say, roughly. Okay. Okay, so this one encodes some action of symmetry, so you can think of it as a stack. It's not a real, I mean, it's not a real geometric stack because you don't have a real groupoid, you have just somehow infinitesimal groupoid in a certain set which is precise.
Would you mind not using stack without definition? Or at least tell us what is a stack. Sorry.
Well, you can think of stack as a space with symmetries, with encoded symmetries. Very, very vaguely at this point, yes? So at this point, just think of stack as a space with some symmetries that are encoded, so like a groupoid maybe. Nothing much more than this.
But maybe you can also define it, I don't know, or it's not good?
It doesn't, it's not so necessary. The point is that you have two kinds of information. One is...
no, that we know from
yes,
the
resolution,
physics part,
yeah.
The mathematical definition may be helpful also at some point. Okay.
That's nothing more at this point. Okay, now, however, this BV complex is the only attempt to kind of describe it in the language of derived geometry was by Costello. Costello, and so how to say this precise? So he considered the longitudinal or the Lie algebroid part as some kind of space in his version of derived geometry. And then took derived critical locus out of it, and he got a BV. Now, the thing is that if you want to interpret this guy as so, okay, you can think now of it as a Chevalier-Allenberg of a Lie algebroid. If you want to interpret it like a space, then you must have a real complex. Your differential must square to 0. Like if you want NQ manifold, your differential should square to 0. Otherwise, you don't have it. And it can happen in the case where the gauge symmetries do not close off the critical surface, that this doesn't happen. So this situation can be explained in two ways. So if you think about Lie algebroid as a kind of a sheaf with bracket and anchor, then what happens is that this sheaf is defined globally, but the bracket is defined only on the critical locus. And if you think of it as NQ manifold, then what happens is the differential doesn't square to 0. So this approach of Costello somehow doesn't have a way to encode such situation. And I will say roughly something near the end about this, although I will have to think more to say something precise, so I will be vague about this point. Another thing, which is not so nice for derived geometry, is that this space of the BV is infinite dimensional. And Costello, again, has his own way of dealing with these infinite dimensions. But if you try to put this in some kind of standard setting of the right geometry, then you don't have this very nice. So one thing that you can do is to go to so-called D algebras and DGD algebras. This is something that, this was part of my thesis, and it's still an ongoing project with Norbert Ponsin to make real geometry out of these guys. And then you can also give a meaning to this derived critical locus, and you can find this local BV of jets. So maybe just let me now say something about how this geometry over differential operators works. So I will start by so just I will first recall what are jet bundles, and then but very vaguely. So if you start with vector bundle, E to M with coordinates x, y, and yi, then you can form a infinite dimensional bundle. And I will say also how it's, so this is roughly, I will be more precise. So J infinity of A to M, and the coordinates will be, so you have the usual coordinates, xi, yj, but you also have additional coordinates for each partial derivative of the fiber coordinates, and also higher. Y, this is j, and so on. So how you think of this? You think of this as inverse limit of as kind of formal inverse limit of finite jet bundles, where you cut the coordinate after too many partial derivatives. And then, so what are? Okay, you have an obvious map. So what it does is, to these coordinates which correspond to partial derivatives, it assigns the partial derivatives of the fiber sections. Okay, but these sections over here can be much richer, because these guys do not have any, and it can be completely dependent after this. So this has much more sections. Anyway, so now what are the functions on infinity bundle? These are functions that depend on finitely many coordinates. Depend on finitely many coordinates. And you can think of them as a direct limit of functions on finite jets. Okay, I think this is all more or less known. But now, what I will now explain is how to encode this thing in the world of algebraic geometry. So this is maybe a bit new with D modules. I don't know if anybody is familiar with this. Okay, so this will then be new. I can erase this. So for simplicity, everything is affine. So everything is affine. Everything is affine. So this part of the construction does not need to be affine. It can be also, you can work with general schemes, it works as well. Later on, we will need really affineness. I will say this, when this will be needed, and the problems that arise when you don't have affineness. But let's say for simplicity, affine, because what's nice with affine schemes is that they are somehow dual to algebras. What does it mean? So every affine scheme is completely determined by the ring of global functions. And not only this, but whatever kind of property you can have with affine scheme, you have corresponding property with algebras. Whatever construction you can do with affine schemes, you have a corresponding construction in algebras. So as long as you stay affine, you don't have to move away from algebras. And this is very convenient, because we know algebras much better than schemes, I guess. Okay, so then we will say, we'll take spec O to be affine smooth scheme. Why this is important? So affine is important, as I said above. A smooth scheme is important because then it has a nice sheaf of differential operators, classical. This is all that's important. Now, as I said, everything is affine, so everything is algebraic. So we don't need sheaves. We need algebraic analogs. So we get just a ring of differential operators. So D is a ring of differential operators. So these are the global sections of the sheaf. They completely determine the sheaf.
Would you mind maybe just saying in some words what a scheme is?
Scheme, this is a place glued out of affine schemes. A space glued out of affine schemes. So you take topological space.
What is a scheme? If you define a scheme by affine scheme, it's not very helpful for me.
I wouldn't go into definition of affine schemes now. But let's think of them as rings, okay? Can we do this? Affine schemes are really opposite rings, nothing more. Okay. Good. Now that we have a ring D, as if any ring, we can form a category of D modules. Okay. And as it turns out, this is a monoidal category. This monoidal category which is kind of unusual because the ring of differential operators is non-commutative. But what you do is you take not tensor product over D, but tensor product over O. And then how you act, so if you have a derivation or a vector field, so derivation of O, and you have something, so A, B, and you act by theta, you act actually by Leibniz rule. So theta A, tensor over B plus A tensor over O with theta B. Now you have a tensor product. You get the category of symmetric monoids. This is monoidal category. This is monoidal category. And it gives rise to category of symmetric monoids. And these are, yes, I mean, the braiding is usual of the tensor product.
Yeah, the question is whether it's so it's symmetric monoidal,
Yes, yes,
not just,
so
okay.
you have the usual braiding as a tensor product with any algebras.
And also another question, if we imagine that spec O is just some kind of, let's say, manifold,
Yes.
then what would be the rest?
So I don't know how manifolds are dual to algebras.
So functions.
This is kind of, this is, I think that this is more algebraic construction. When you want to do such things with manifolds, you work with jets.
Okay.
D modules are more used for algebraic geometry or for complex geometry or these kinds of settings. No, not so much for smooth.
No, I just want to like understand what was going on. So what would be jets in this picture? Or they are not? They are not here
Jets
yet?
will come next.
Okay. So what would be the category of
Which category?
this monoidal category of D modules?
Sorry.
The monoidal category of
Yes.
D modules. So it would correspond to what? Like on the smooth side? So theta.
I wouldn't like to say something stupid.
So theta should be just a vector field, right?
Yes, and then if you have if you compose them, then
You have higher order
you
differential
do
operators.
yes, higher order. Exactly.
And so what was the monoidal? Yeah, okay.
So you have tensor product. So the tensor product over O.
Yeah, I know, but yeah, so it's still the same question. So how can we imagine this monoidal category in some settings that at least I know?
Maybe sections of vector bundles or something?
So it would be, so it's just vector bundles?
Okay, I mean, of course, functions, you can act on them. This is an example. You see it here also, because O is D module. You can, if you want to. You can have such examples, but so what will be the entire category? This I don't know what will be in differential geometry. Like you can find examples, but what will be the category? I don't know. But let us continue, and then things will become interesting when we get to jets, I think. Then you will see what really goes on. Okay, so you have category of the algebras. And you have category of O algebras. And you can just forget that you have a D module structure. Okay? O algebras, yes, or yeah. Yes. Okay. So these would be. So if you have map O to A, this means that you have map A, spec A to. Yes. So this will be like bundles. Because when you go to spaces, you're opposite. So if you have a map from O to A, and this means having O algebra, then this means that you have a map from spec A to spec O. So these will be vector bundles. But I think things will become clearer on the first example. And you have this, so you define jet functor as the left adjoint to the forgetful functor. And it turns out to give a quite good description of jets. I mean, it seems simple, but it encodes actually a lot of things. So to explain this, let me first mention another adjunction. So from D module to the algebras. Here you have forgetful functor. So the left adjoint to the forgetful functor that goes from the algebras to D modules is the following. So SO of A is equal to the direct sum A tensored over O tensored over O A. So this is over n. This is n times. And then you quotient by the action of the symmetric group. So it's symmetric tensor product. It's defined like this. And it's defined the same way as also the... Okay, let me continue, and then maybe with the example everything will become clear. So, example. We'll take O to be just polynomials in Xi. So this is like an affine space, if you want. And then A to be like a trivial vector bundle over O. So O of Yi. Now, so what are the polynomials in Yi? This is what you get when applying a symmetric algebra functor to the module generated by Yi's. O times Y. Okay, I's. But now this is not the one above, so this is another one. This is SO that goes from O modules to O algebras. I mean, as you expect, a free guide, a free commutative algebra that you get from a vector space, you want it to be a polynomial algebra, right? Okay. Good. And now you want to know what's the J infinity of A. So what is it? It is equal to J infinity composed with SO of IO times YI. Yeah? So I just used the above line. Okay. Good. So now you can look at this composition of a junction. O mod D mod D algebras. So this is, as we said, SO. This is forgetful. Forgetful. So what is this thing? Well, if I go from modules over one ring to modules over another ring, my free functor is the tensor product. This is, I think, standard. But now you see interesting thing. So this guy, this functor, is also left adjoint to the forgetful functor from the algebras to O modules, as is this composition. Okay? So you have forgetful factor from the algebras to O modules. You can look at it as the composition of these two forgetful functors. But you can also look at it as the composition of functors that go from O algebras, the algebras to O algebras, and then to O modules. Okay? And if you take this other approach, then the left adjoint that you get is this one. Okay? Should I write this in more details? Okay, so you can do this. So O mod, O alg, D alg. Forgetful, and then this is really SO J infinity. Now, composition of a junction is a junction. And since here the right adjoint is the same, the left adjoint should also be the same up to natural isomorphism. But this means that this composition here is the same as composition of over here. So SO composed with the tensor O that acts on direct sum of O, Y, I. Okay? But then there's something that you know how to compute. So you tensor this with D, you get direct sum of D times Yi, and you take SO. So then what is this? This is the polynomials in Yi, where each Y can have a differential operator attached. Okay. So how would elements of this guy look? So it would be x1 times y1 plus x2 times y2, where these are differential operators. Or you can also multiply, right? Times x3, y3, and so on. But now if you look at what x is and what I is, you can write this as the polynomial. So what you can have x's, you can have yj's, and you can have the guys with attached differential operators. But now you can use this tensor over O to push out the functions out of these operators and to end up with pure partial derivatives. So dx, I, yj, and so on. You see that you get really the functions of the jet bundle. So you have polynomials in each of the variables of the base space, in each of the variables of the fiber, and for a variable for each partial derivative. And another thing that you get, so this is definitely a D algebra. So you have an action of differential operators. So how do differential operator act? If I take d xi and I multiply them with this guy, dxj, yj, so what will happen? I mean, this differential operator will just multiply the differential operator in d, right? Multiplication in d times y, so how you multiply this by differential operator? You compose it with the differential operator over here. Right? So you get d xi dxj yj. But now if you look at these guys, these polynomials, what happened? So you kill this one, and that is the one with extra differential operator. But this means that you actually act as a total differential operator. So if you have any function, the xi of f, this will then be the xi, I wrote it here, sum over multi-indices d xi sigma y times df over dx sigma y. So you kill one with the smaller and add one with the bigger. So it's really really total differential operators. So dx is total differential operators. This is kind of nice. And now we want to encode BRST differential in this, right? And BRST is a kind of chain complex. So if you want to do this, we need the chain complexes in this setting. Now you have a category of D modules. As a category of modules over any ring, you can construct chain complexes. Or chain complexes of D modules. Well, so differential will be a differential. Differential is D linear. Now again, you have a monoidal structure.
Sorry, how does this work from the D modules to the chain complex? What kind of map do you have there? Or what kind of chain complex?
No, the category of D modules gives I mean, if you have any abelian category, you can form the category of chain complexes, right? This is not map. This is just if I have category of D modules, I get for free category of chain complexes. Mm-hmm. I have monoidal structure, which is the usual one for chain complexes. So A tensor OB n is equal direct sum of A K tensor OBL K plus L equals n. And now D acts as non-graded derivation or even derivation. So I have this action from before, and everything new that I'm saying is that you don't have any signs, which is kind of logical because D is even, it's in degree 0. Okay. And then the differential, of course, acts as a graded derivation. But since you have a monoidal structure, you have also the braiding, which now adds a sign when you interswitch two odd guys, right? So you get the graded commutative monoids or commutative monoids. So the algebra, this is commutative monoids in a chain of the okay. So these are basically the same thing as DGO algebras, it's just that they have the action of differential operator, which doesn't care about the gradings. Nothing new here. Okay. Okay, so now let's see what we have in BRST. So we had fields. mu AFX. And the BRST differential was mapping them into D AB mu eta B, and then D of d of eta A is here I have C A B eta A eta B. So I mean, this thing, if you switch to fiber, if you switch to jet bundles, then this is this is fiberized, right? Because this is differential operator. So this is a differential operator. Operator on base with coefficients in fields. Okay, so let's see how to encode it. So if you think very naively, as this guy being kind of polynomial, so you take spec A as a field bundle. Field bundle, so that then A you can think of as polynomials on A mu A. And this differential becomes a differential on this differential on infinity jet of A tensor with SO with this free guy d times dB with the differential. Okay, do I need to explain more on this, or is it okay? A bit more, okay. So, you can think very concretely about this guy, so you can write down what it actually is. In formulas. I mean, so this guy is where it is. So this guy is the A B mu is the partial derivative with respect to mu delta AB minus F ABC AC mu. So you can set D of A mu A to be equal to. So here I can just take. So this is the mu in B. So this is the guy here, right? And then I add FABC A C mu also maybe. Right? And then this guy is also here. So here the differential operator is trivial, but the tensor product is non-trivial. Another question that's kind of interesting here is that this somehow seems to be like a good notion of Lie algebra in this setting. So a question which I didn't work on, but I think it should have an answer, and very easy answer. So in comparison, with standard notion of Lie algebroid, in algebraic geometry, in algebra. And these are Lie-Reinhardt algebras. Lie-Reinhardt algebra, so to find the bracket structure, that would give as Chevalier-Eilenberg complexes a tensor SOVD, where V is finitely generated projective D module. Similar thing is done in differential geometry by in jet setting by Kislev and van der Loor. They define some kind of variational Lie algebroids on jets, and they linked it to kind of Chevalier-Eilenberg that they made. But I think that this should be even easier than that. But okay, this is not real derived geometry. The derived geometry comes when you have something to derive, right? And if you want to be able to derive something, then you need some kind of homotopy theory. And this homotopy theory... Huh? This homotopy theory we get. And this is it's not one theorem, it's many theorems, but somehow combined into one sentences. So, theorem. This is Debrina, Fonsan. And this is in two papers, so one is from 2018, the other one is from 2019. And the category of DG D algebras is a proper model category with quasi-isomorphisms as weak equivalences degree-wise surjections as fibrations and relative Sullivan algebras and retracts of relative Sullivan algebras as cofibration. Maybe let me first explain what relative Sullivan algebras are, and then should also explain what model categories are, probably. Okay. Okay, so relative Sullivan algebras. Are morphisms. This is relative Sullivan D algebras, because they're over D. So, because usually this is in homotopy theory, so D algebras, relative Sullivan D algebras. D algebras. So morphisms A, these are O, SO, direct sum, E over E, DAE, with a differential, such that so indexes here are ordered such that in the E, so you can say that E is an ordinal, or indices. Indices I are well ordered. Well ordered, and D of AI is in A tensor O. So direct sum I in I, J less than I, D times I, J. So they're semi-free, they're free as graded D algebras, but this basis must behave nicely with, this basis of this free guy must behave nicely with respect to differential. So you cannot have differential going anywhere, but you must have the kind of ordering that the differential will respect. Okay.
Sorry, just why do you say they are morphisms?
Oh, sorry. This is injection, right? So this is A goes to A. Maybe just say a few words what model categories are and why they're useful. These are categories with 3 classes of morphisms. We have weak equivalences, and you usually denote them like this. You have fibrations. You denote them as surjections. You have cofibrations. You denote them like injections. And they satisfy some axioms, which I will not say. Except I will say one axiom. This is the axiom of factorizations. So any map A to B can be decomposed as A have trivial cofibration to A prime and then fibration to B. So what this means that this is in the same time the cofibration and the weak equivalence, right? So I have weak equivalence and cofibration. And this one is just a fibration. And the other way around. So A, B prime, B. It doesn't have to be. I mean, so the idea is that the This is like the inclusion, right? I mean,
It's not surjective. The first map is surjective on B, right?
no. So, I mean, what any map you have, I can first explode it to something bigger by injection, and then kind of find the surjection to put it back to B. This is the idea.
But if it's only surjection in the beginning, you cannot.
Why not?
If the image of A is a real subset of B, a proper subset of B, then it's not this problem.
Why? I mean, with potatoes. I mean, you explode it in the middle, so. So a nice consequences of these axioms are the following. So if you take initial object, initial and final, so this category should always have initial and final objects. I didn't write it. So this is under these axioms that are not mentioned. Then you can take a map from the initial object to A, and you can decompose it as a cofibration and trivial fibration. And you call this guy a cofibrant replacement. So it is in a sense replacement. Sorry, I forgot. This should be weak equivalence and the fibration, so trivial fibration. So this is a kind of replacement because this is weak equivalence. And it's called cofibrant when the map from the initial object to it is cofibration. So cofibrant means that map from the initial object to it is cofibration. And you can do the same thing you can get in the same way fibrant replacement. This is fibrant replacement. And these are very useful for doing homotopy theory. So you have Ken-Brown's lemma. Now I may state it a bit wrong, but not too much. 5 minutes, okay. I may state this a bit wrong because I don't have this slide. I didn't plan to speak about model categories, but the point is there. So if a functor preserves weak equivalences, cofibrations, and trivial cofibrations, then it preserves weak equivalences between cofibrant objects. And this, you have then the notion of Quillen adjunction. So, A, B, G. So if this functor if this left adjoint is such, then this means that whatever kind of cofibrant replacement of a guy in the source you take, you will end up with this means that if I take any two cofibrant replacements of this guy, and my factor is such, then their image here will also be, their images will be weakly equivalent. Because if this guy preserves cofibrations and trivial cofibrations, it preserves weak equivalences between cofibrant objects. So if I have two cofibrant objects that are weak equivalent to this guy, then there will be weak equivalent here. So this gives derived functors. And now, in the time that I have left, I will try to make a kind of very, very toy example of a derived critical locus to see how these kind of things gives rise to BV kind of structures. But it's very trivial, so I will not even have ghost, I will just have fields and antifields. Maybe no, since I have only 5 minutes, I will use the time for better reasons. So, what can I say better? So, I have this. Just let me. It's nothing that I want to say. Okay, so. Okay, we had it, I erased it. But we had it, the category is proper. I wrote this at some point. And it's some, it's some nonsense condition on its own. But it gives a nice way to compute homotopy pushouts. And then if you think of derived critical locus as a kind of homotopy pullback on spaces, then if you go dual to algebra, this becomes homotopy pushout, at least if you are over affine, guys. And using this kind of reasoning, you can really get Dion shell BV, let's say. I will not explain now, but so I will explain what we still didn't do and what we can do. Now, how are derived stacks? So see, okay. So now we have a good algebraic setting. We have a model category on DGD algebras, which means that we can do whatever we want in the affine setting. But we cannot do whatever we want in the non-affine setting. And the theorem that we had, it works only when your base space X is affine. If it's not, then it doesn't work. And this theorem seems to be crucial if you want to do derived algebraic geometry. So schemes. So you can think by functor of points. As map from commutative algebras to sets, which have a kind of sheaf condition. Now, if you want stacks, you still go from commutative algebras, but now you go to simplicial sets. So you have a model structure here. It induces the model structure on the space of functors. And then you further change this model structure, you boost with localize it, whatever it means, with respect to hypercovers to get kind of sheaf condition. And then this guy, so you see that there is no derived setting, that there is no DG thing here, but there is this simplicial set, which means that it is, so it's stuck. Okay. So it encodes actions, but it doesn't encode any derived information. And then you have derived stacks. You can think of them as functors from DG commutative algebras to simplicial sets. And now you have a model structure here. You have a model structure there, so you cook a model structure out of the both on the category of functors. And then you boost with localize with hypercovers to get the kind of sheaf condition. And so this is how we would like to build a stack. So but what Stoyan does, then, Fine. So he replaces this. Replaces DGCA by a sufficiently nice category C. A sufficiently nice category C. And then gets a kind of derived stacks in any setting he wants. And we think, so we want to do this with our DGD modules. And then we will be able to get geometry which will contain both stack and derived information and be good for jets. But the problem is that we cannot relax the condition that our base space should be affine. And I think once we finish this thing with the affine, it would be very interesting to see how we can then glue maybe these stacks that are already built over different guys. So we cannot glue them and then build stacks, but maybe we can build stacks and then glue them. But anyway, this is just something that's very far away. Okay, thank you.